Hey, Science 30s, and welcome to the second half of the Electromagnetic Energy Unit. We're going to start a discussion today on the electromagnetic spectrum. It's going to be a two-part discussion on this topic with topics 2.1 and 2.2 in the textbook. You're looking at Unit C, Chapter 2 for this section. It's going to be pages 410 to 459 in the textbook. And as similar to the first half of the unit, you're going to be using pages 2 and 3 of the Science 30 data booklet to get you through this material. Well, technically, I'm going to take a look here. Yeah, you're going to need page 2, but mainly page 3. That's the big page you're going to need for this half of the unit. The first half of my discussion today, again, about the electromagnetic spectrum, we're going to break down what is light, what are the different types of electromagnetic radiation and waves that are out there. These are terms you've probably heard before in maybe an earlier science class. And even if you haven't taken these in an earlier science class, a lot of these electromagnetic waves you're going to be familiar with by name, and we'll go through them today to kind of break them down one at a time. One thing you can definitely look at for this section at the bottom of page 3, there is an entire electromagnetic spectrum diagram there, which basically tells you the order of each of the types of electromagnetic radiation from the longest wavelengths, which are your radio waves, all the way to your shortest wavelengths, which are your gamma radiation waves. And we'll discuss all of that today. So first of all, what is an electromagnetic wave? Why do we consider light, and visible light is a form of electromagnetic radiation? It is an electromagnetic wave. Well, what is an electromagnetic wave? Well, an electromagnetic wave, by the name, and based on the first half of our unit, that should be kind of obvious. It's a wave. It's actually two waves in one. An electromagnetic wave is essentially light travels in a sort of a dual electric magnetic field configuration. So a light, I guess a light wave would propagate as an electrical field. And as we're well aware, electrical fields will create magnetic fields, and magnetic fields will create electrical fields. So they're going to travel in tandem with each other. But here's the kicker. The electric field and the magnetic field, and my diagram isn't so great up here, but if you've got the notes in front of you, on your computer, you can see the diagram right here. They are traveling in 90-degree angles in relation to one another. So for that reason, an EMR, an electromagnetic wave, which produces electromagnetic radiation, and I'll get to that in a couple seconds, is basically what we call a transverse wave, because there are two fields inside the wave, an electric and a magnetic field, that are at right angles to one another, and that's how the wave sort of propagates itself in a particular direction. Now, as this wave moves forward, it is going to release, depending on the type of wave or the type of electromagnetic wave it is, it's going to produce either anywhere from small amounts to large amounts of electromagnetic radiation. And I'll discuss which waves produce more radiation a little bit later in today's discussion. But for now, be aware that all electromagnetic waves, whether they're visible light, radio waves, microwaves, infrared, UV, gamma, Xrays, they all produce some amount, and some produce more than others, of electromagnetic radiation. Now, what does electromagnetic radiation? Is there a commonality to the electromagnetic radiation that's being produced? Well, there is. All forms of electromagnetic radiation have several things in common. The first thing is that, unlike when we think of a wave, normally when you think of a wave in a water, let's say you throw a pebble in a pond, and it creates ripples or waves out from where you hit the water with the rock or the pebble. Normally, waves require air, or you require water, or you require some kind of a medium to propagate the wave through. There has to be something for the wave to interact with in order for that wave to actually move through. In the case of electromagnetic waves, which are producing electromagnetic radiation, these forms of energy do not require any form of a medium to travel through. They can travel through a vacuum, i.e. they can travel through space. Sound waves do not travel through space because there's nothing for those waves to interact with in space. The old adage, if you've seen the old classic 1979 movie, I believe, Alien, The tagline for that movie was, "In space, no one can hear you scream." Well, that's true. In space, there is no sound because there are no air particles for sound waves to propagate off of. But electromagnetic waves work differently because they're a different type of wave. They can run through a vacuum and not have any issues at all. So that's one thing that all EMRs all can travel through the vacuum of space. The second thing is the speed at which they travel. When they're traveling through space, and this was proposed by Albert Einstein, here's good old Albert Einstein over here, when he proposed his theory of general relativity, he also came up with a very famous equation, which we'll get to in the next unit. Actually, no, we'll get to it in the next unit, E equals mc squared. But he also theorized that the speed of EMRs, or the speed of light, is the universal speed limit. Nothing can travel faster than the speed of light. And the speed of light, or the speed of EMRs, because EMRs, light is a form of, is an EMR, these all travel at the speed of 3.0 times 10 to the 8th meters per second. Now, do you have to memorize that number? Well, no, you don't, because here it is on your data sheet right there. Speed of electromagnetic radiation, air or vacuum, 3.00 times 10 to the 8th meters per second. And he designated the speed of light, or the speed of these EMRs, with a letter which was C. C is the letter that's designated for the speed of light. But we can also, in this unit, discuss the speed of light as velocity, because technically it would be the velocity of light. So if we were to plug it into a formula that we needed to calculate the formula based on the speed of light, we could plug it into a formula that uses V. And I will get to some formulas here in a couple of seconds. Another thing that all EMR have in common is that different medium will slow them down. For example, if light hits water, you get a process known as refraction. You may notice that when you're underneath a pool and you're looking up above you, things look like they're in, the light's sort of a little bit weird. Things are not where they really are. If you're looking into the water from above, you might be able to reach down and let's say there's a fish in the water or a frog underwater, you might reach down thinking that's where the fish or the frog is, and then you might realize that the fish or the frog is slightly off to where you actually see it. Well, that's a process known as refraction. As light enters into different medium, it actually bends. It actually, its path changes. So if light kind of comes into a water, and here's my water, I'm going to do a better angle here. Here we go, better angle there. So here's my water. It's kind of tough to do here on the board, but here comes my light onto the water. What's going to happen is the light is actually going to bend at a different angle as it enters into the water. So you're going to get a slight bend of the water as it actually, what happens is it slows down. As that light hits that thicker medium of the water, it actually loses some of its speed. It's 3.00 times 10 to the 8th meters per second, and that actually causes the light wave to bend. And we call that process refraction. And I will get more to refraction later. Before the end of the year, we will cover refraction. In fact, we will discuss refraction in the second half of our discussion about electromagnetic energy next day, which is the astronomy topic, which will be 2.2. And then the last thing that I've already mentioned is that all EMRs travel as transverse waves, which means that they are dual electric and magnetic fields that are interacting with each other at right angles or 90-degree angles from one another. That is what all EMR electromagnetic radiations have in common with one another. Now, are there some formulas that we can use to calculate, properties of electromagnetic waves? Well, there are. The first thing that I'd like to discuss is actually the formula to calculate the length of a wave. How do you actually calculate a length of a wavelength of an actual electromagnetic wave? Well, what is a wavelength? First of all, you've probably heard the term wavelength before, but what is a wavelength if we're defining it by definition? Well, a wavelength is essentially the length of one cycle, and one cycle is on the diagram here. A cycle would literally be if the wave is sort of doing this and doing this, is going up and down and up and down. That's what waves do. Well, a cycle would essentially be the time that it takes for it to do that. So basically, when it starts here, comes back, and then until it gets back to that starting point again, that distance from here to here, that is my wavelength. We refer to wavelength with a symbol that actually looks very similar to that. It's a Greek letter known as lambda. Lambda is the symbol that we use to designate wavelength in wavelength equations. And that is the symbol that you should get fairly familiar with. And it is listed on your data sheet here on page 3. There it is, the wavelength of light right there. So we're good to go there. Okay. So how do we calculate a wavelength? How do we calculate lambda? Well, the formula for lambda, and we're going to calculate lambda in meters, so the actual number of meters that a wavelength is, it's going to be the distance of the cycle, the distance that it travels, pardon me. So if I can calculate, okay, it's traveling a distance of 5 kilometers. That's how far the wavelength, or that's how far the EMR, the electromagnetic wave, has traveled, and how many cycles have occurred during that length of time, or that distance, I should say. So what we're looking for is the distance that has been traveled by the electromagnetic wave, the total distance. So if it's traveled from, let's say, here to the fishing game pond, that would be a distance of, let's say, 2 kilometers. And if in that 2 kilometers we've had 1,000 cycles that have occurred, well, I would say I've got 2,000 divided by 1,000, because it would be 2,000 meters is 2 kilometers, divided by 1,000 cycles. That means that each cycle would be a total of 2 meters in length. So that would be our lambda value. So the length of the wavelength there would be 2 meters, based on the fact that the wavelength had traveled, the electromagnetic radiation has traveled 2 kilometers, which is 2,000 meters. It's done 1,000 cycles in that period. 2,000 divided by 1,000 is going to give me 2 meters in total. That would be how I calculate it. Now, this formula is not found in your data booklet. So you might want to jot this one down, or have this one in your data booklet to have for your work in this unit. But this is the formula. Lambda is equal to distance in meters divided by the number of cycles. All right. Let's do a question that's an example here. It's in the notes right here. So if you've got your notes up, maybe pause me right now or grab the notes if you haven't got them. I'm going to do it off the note sheet, not off the board. I've got an example of, there are 3.25, so 3.25 cycles that occur over a distance of 14 meters. So I've got an EMR, I've got an EMR that's traveling 14 meters. And it has 3.25 cycles over that 14 meters. Calculate the wavelength, the lambda value of the EMR. Pause me right now if you need to. I'm about to go over the answer and expose the answer down here on the sheet for you. There we go. Well, the formula for lambda, as I just mentioned, is your distance. So your distance is going to be 14 meters. We're going to divide that by the number of cycles, which is 3.25. So 14 divided by 3.25 is going to give me a value of roughly 4.31 meters. And be aware that the value that I gave you was 3 significant digits. There was 14.0 was the value that was actually in the question. So we're going to round that to 2 decimal places for 3 significant digits, which is going to be 4.31 meters. That would be the lambda value on the question there on the page. All right, a couple more equations to get you finished up here on the equations, and then we're going to get to the actual electromagnetic spectrum, discussing each of the different forms of electromagnetic radiation. Okay, so we can also describe EMR not just by their wavelength, but by their frequency. And the frequency is measured in a unit called hertz, and it is represented by the letter F. So F would be a little f, would represent frequency in an equation. What is frequency? A frequency of a wave is how frequently a cycle passes by a stationary object. How frequently do we see these cycles passing an object that isn't moving? That would be the frequency. And how do we calculate frequency? Well, our frequency equation, and this equation is also not in your data booklet, so you may want to write this one down as well. The frequency equation is frequency in hertz is equal to the number of cycles that we see passing a stationary object divided by the time that it takes for those cycles to pass by the object. And usually time would be represented in seconds. So we've got hertz would be our units for frequency, and in this case our time should be in seconds in order to make everything work in the equation that we need to. So let's try an example. Here's one that's on the note booklet as well. Hopefully you haven't looked at the answer below, but here's the question. I've got 4 cycles of an EMR are going to pass a detector in 4.0 times 10 to the negative 6th seconds. What's the frequency? So again, I've got 4 cycles passing the detector, and the time that it takes for those 4 cycles to pass is 4.0 times 10 to the negative 6 seconds. See if you can calculate the frequency of the wave. Pause him right now if you need to. Here comes the answer. Here's the answer. I'm going to use my frequency formula. It's going to be the number of cycles on top, which is 4. I'm going to divide 4 by 4.0 times 10 to the negative 6 seconds. That is going to give me an F value of 1.0 times 10 to the 6th hertz. And I can convert that if I wanted to. Sometimes we use the designation megahertz. Megahertz would be a million. So if I took 1.0 times 10 to the 6th divided by a million, if I wanted to do that, I could calculate the 1.0 megahertz, which would be the frequency. I could also divide 1.0 times 10 to the 6th by 1,000 to get my kilohertz value, and that would be 1.0 times 10 to the 3rd kilohertz. So again, normally your answers are going to be in hertz, but just be aware that hertz, just like kilometers or meters or grams or liters, like any of the other measurements we have, we can designate in kilohertz, megahertz, microhertz, millihertz. There's all sorts of values that we can assign for frequency. So just keep that in mind. So there you go. There's another one. And then, so what's the big deal of knowing what our wavelength and our frequencies are? Well, we can also plug them into an equation that you do have in your data booklet. And the equation you do have in your data booklet is right here. There it is. 2 little unassuming formulas there for your wave formulas. And that formula is essentially called the universal wave equation. So if I know 2 of my 3 properties of a wave, and we know that all EMRs are going to have a constant speed in space or air of 3.00 times 10 to the 8th meters per second. We can then use 2 values if we always know the speed of a wave if it's in the vacuum of space or in air. But if I know either the wavelength or I know the frequency of the wave, I can calculate the other value. So if I know the frequency of a wave, I can automatically calculate the wavelength of that wave because I'm assuming that the wave, if it's traveling through space or air, is traveling at my 3.0 times 10 to the 8th meters per second. The equation we're dealing with is this one at the bottom here. Velocity, or in this case C, because C would be the velocity of the EMR, the speed of light, is going to be V equals lambda times frequency. So if I take my lambda, I take my frequency of the wave, I should be able to take those together, multiply them together, and I should always get a value of 3.00 times 10 to the 8th. So because I know the speed, I can use the speed. If I know the value of either lambda or frequency, I can calculate the other value because I always assume that I should know that the speed of light is that 3.00 times 10 to the 8th meters per second. So let's do an example using this, all right? So for example, an excited atom in a neon sign emits electromagnetic radiation with a wavelength of 6.4 times 10 to the negative 7th meters. So I'm going to repeat that number. The wavelength, or lambda, is going to be 6.4 times 10 to the negative 10th meters. That's my wavelength. Based on that information and using the universal wave equation, can you calculate the frequency of the EMR? I'm going to give you a second to do that. Pause me if you need to. And I'm going to spill the beans here right away. All right. So I'm going to use my universal. Wave equation. I'm going to rearrange it. I can rearrange the equation a little bit here. So in this case, as you can see on the page, if you've got the page in front of you, it's been reconfigured to frequency equals velocity divided by lambda, or frequency equals c divided by lambda. Same thing. C, V, in this case, is going to be 3.00 times 10 to the 8th meters per second. So I'm going to plug all that information in. Frequency is essentially going to be equal to 3.0 times 10 to the 8th meters per second divided by 6.4 times 10 to the negative 10th meters. That's going to give me a hertz value. And by the way, hertz is designated as 1 over s. That's how we get, so it's 1 over a second is a hertz. And in this case, my hertz value is going to be 4.7 times 10 to the 14th hertz. So that's basically going to be the math in this portion or this topic of the unit. So hopefully that all makes sense. Three equations that play in. You've got your lambda equation, which is distance divided by number of cycles. You've got your frequency, which is number of cycles divided by time. These two equations are not provided in your data booklet, so maybe put those down somewhere, jot them down. Though the equation that is provided in your data booklet is the universal wave equation, where I can combine my frequency and my lambda values into the equation. Velocity of an EMR, or C, is equal to lambda times frequency. So those are the three equations that you should be familiar with. The remainder of today's discussion is just going to basically be looking at the electromagnetic spectrum. Now that we've talked about how we can classify EMRs based on frequency and on wavelength, what the commonalities are between each of the electromagnetic radiations that are out there. Let's take a look at the differences between them, because each area of the electromagnetic spectrum, depending on the wavelength and the frequency of a particular EMR, that's going to determine what it's classified as. So we classify the different electromagnetic radiations based on their wavelength and therefore their frequency. And generally speaking, the electromagnetic radiation starts with longer wavelengths that have lower frequencies and therefore have lower energy. Generally speaking, the longer the wavelength, the lower the frequency, the less energy that's being propagated by those electromagnetic radiations that are being released by the electric and the magnetic field. As I go through the electromagnetic spectrum from one end to the other, the trend is the wavelengths are going to shorten, the frequencies are going to increase, and therefore the radiation is going to increase. And that trend is basically shown here on the diagram. Here are the ones with your lowest wavelengths on this side. These are the ones with the longest wavelengths on this side. You should be familiar with the concept that a longer wavelength indicates a lower energy to the electromagnetic radiation that's there. The higher the higher the wavelength, or the smaller the frequency, the higher the frequency, I should say, or the shorter the wavelength, that's going to indicate a higher level of energy. And those are the electromagnetic radiations that we have to be more worried about. And as I go through the discussion today, my discussions are going to start with the electromagnetic radiations that have the lowest frequency, the lowest frequencies, the longest wavelengths, then we're going to move up from lowest sort of the highest wavelength. Longest wavelength to shortest wavelength, lowest frequency to highest frequency. That'll be the trend of my discussion here today. If you want to take a look at the electromagnetic spectrum before we get started, take a watch of this video. Professor Dave explains it quite nicely in just a few minutes. That gives you kind of an introduction to the electromagnetic radiation spectrum. And let's take a look at it from here. So the first one on the plate is going to be radio waves. Radio waves are the lowest frequency and the longest wavelengths of electromagnetic radiation out there. They are primarily used for communication. We're dealing with AM and FM radio, which you're probably very familiar with. There are really no energy levels are extremely low. Effects on biological tissues, there's really none. Interesting trivia. In order to receive radio waves, you often require an antenna. You may have heard of an antenna, because they can't penetrate metal objects very well. So that's why you use an antenna to actually get the radio wave into a metal object, because they have such little energy, they can't necessarily enter one of these older school radios that would have had these antennas, or back in the day, or even in your car. You use an antenna to get the radio into your car, because the metal of your car can sometimes be a problem to get the radio waves in. An AM radio wave is a longer radio wave than a FM radio wave. That's why AM radio is able to travel longer distances. You may notice that if you leave Edmonton, FM radio stations will disappear before you lose your AM radio stations. It's because there's a longer wavelength. And the longer the wavelength, the easier it is for it to get around and up and around hills that might cause blockages in signal. Radio waves can also be used in something called a magnetic resonance imaging system, or an MRI. This is going to allow you to produce very detailed images inside your body that can basically be used to diagnose, cancerous growths in the brain, that kind of thing. And one last thing, we'll discuss a little bit about this, but there are what are called radio telescopes, which basically pick up radio waves. that emanate all the way back to the Big Bang, the formation of the universe. So that we do have telescopes that are basically looking not for visible light, but looking for radio EMRs coming from the depths of space. And because they are the longest wavelengths, they can travel the greatest distances unimpeded. So they are generally very difficult to hear because or see, however you want to perceive it, but they are out there. So we can definitely pick those up by using very large radio telescopes here on Earth. The second one on the list is going to be microwaves. Microwaves have a slightly shorter frequency than radio waves. They're used primarily for radar, satellite communication, for cooking food with microwave ovens and such. Energy levels are going to be moderate. Effects on the biological tissues they can cause cataracts in your eyes. They do have a little bit more energy there. Interesting trivia, microwave ovens are going to heat up your food by vibrating molecules of water. That's how microwave ovens heat your food up, by vibrating water molecules that are in the food. And the reason why you should never put metal objects in a microwave oven is that the metal reflects the waves, which can damage the oven by heating up excessively or by creating electrical fields that cause sparks and possibly a fire. So that's why you don't put metal objects in your microwave oven, but that would be a good thing not to do. Infrared radiation, moving up the chat. We're moving up here. These guys have energy levels that are low to moderate. They are good for heating. That isn't up here, but infrared radiation, I would also have heating lamps up here. That's a great use of infrared radiation. And by the way, you should know uses of all these forms of electromagnetic radiation. The government is expecting you to know that, and I will be quizzing you on that and testing you on that later in the unit. Effects to biological tissues, well, you can burn yourself. If you get yourself too close to a heating lamp, you can actually burn your skin. Interesting trivia about infrared. Infrared literally means inferior to red. This is because it has a slightly less energy than red, which is at the bottom of the visible light spectrum. So it's just below red in energy. So red light would be just above infrared. So that's why we call it infrared, inferior to red. And then we also, one of the really common uses for infrared now is for beaming, which is used in a lot of remote controls in your house for your TVs and your Blu-rays or whatever remotes you're using for devices in your home. A lot of them are using infrared light to actually create the communication between the devices. That brings us to the middle of the electromagnetic spectrum. We get to visible light, a very small section of the visible light. That's a spectrum that you and I can see. We cannot see any of these forms of radiation or any of these forms of radiation. We can see essentially from red to basically violet. How do you remember the order of the colors on the visible light spectrum? Here they are. Easy way to remember it is to remember the very famous scientist Roy G. Biv. So Roy G. Biv means that it's Roy, red, orange, yellow. G is green, B is blue, I is indigo, and then you've got V is violet. So those are the colors that are on the visible light spectrum. Interesting trivia: the shortest wavelength is going to be violet. The longest wavelength is going to be red. Sir Isaac Newton came up with the idea for 7 colors in the visible light spectrum based on the 7 days of the week. So that's why there are technically 7 colors in the light spectrum. One interesting thing, and this is, you want to watch this video because it's true. The color pink doesn't exist. If you don't believe me, watch the video. They'll explain why. But the color pink, it's an illusion pink. But watch the video. They'll describe why pink is an illusion. Einstein proposed a radical adjustment to the idea that visible light was an electromagnetic wave. This is the interesting thing about the physics thing. Einstein believed that light is emitted in bundles of energy known as photons. So he proposed that light actually acted like a particle. So that's sort of the thing with light, is that it, in some respects, it acts like an electromagnetic wave, but in some aspects, it actually does exist or work like a particle, like a discrete bundle of energy. So if you're interested about whether light is a wave or a particle, because there's sort of a lot of debate raging about this, like, is it both, is it neither, is it one or the other? If you're interested to just see a little bit of the debate behind that, watch this video here, which will discuss a little bit more about whether light is a particle or a wave. But for the purposes of our course, just be aware that we are referring to light as an electromagnetic wave that can actually bundle as photons. So there is a little bit of an aspect to both there. But the majority of our discussion about light is going to be based off of its relationship with the electromagnetic spectrum, which puts it clearly as an electromagnetic wave in that respect anyways. All right. A couple more before we're done. UV radiation, now we're getting into the higher forms of radiation. Ultraviolet radiation literally means better than violet. Ultraviolet means better than violet because it's slightly higher in energy level than the violet on the visible light spectrum. There are some insects that can use a UV light to look to find where the pollen is on plants. If you look at plants and flowers under UV light, they look very different than what we see with visible light. They're almost like little landing pads that kind of direct some of the pollinators to where the pollen is, where they can get the nectar off the flower. What are some of the biological issues with UV? Well, UV does help us produce vitamin D, but it can also lead to forms of skin cancer, especially when you get to the higher energy forms of UV. And there are 3 types of UV rays that we've already talked about a little bit here in the course. We talked about the ozone layer back in the chemistry and the environment unit in Unit B. UVA causes wrinkling of skin. That's the lowest form of UV radiation energy. A possible link to skin cancer. UVB causes sunburns and cataracts. Also a link to it has a proven link to skin cancer. And UVC is now what we call ionizing radiation. It is a very dangerous form of radiation. It's a physical mutagen that destroys DNA, and it will basically this is the UV radiation that the ozone is really blocking. The ozone layer is helping to block these UVC rays. They're the ones that we're trying to really stop from getting into the lower atmosphere. UVA gets through almost, unimpeded, but it has the lowest amount of energy. UVB has the middle amount of energy, but anything above UVC, which is the highest form of UV radiation, including X-rays and gamma rays, these are all forms of ionizing radiation, which are extremely lethal, damaging to DNA and to life on Earth. These are things that we just have to really be careful about not getting, hammered with I guess, at ground level. They're not things that we want to get exposed to. X-rays. X-rays are another beauty. And again, you all know what an X-ray is because, you get X-rays to see inside your body. Energy level on X-rays are high because they are forms of ionizing radiation. It passes straight through flesh and is only stopped by bone or cancerous tumors are the only things in your body that will actually stop X-rays from going through. That's how we create X-rays. You can see the bones in your body because they're stopped by X-rays. They were discovered in 1895 by Roding is a guy's name who discovered them. He actually never finished high school, but he discovered X-rays. So I guess the guy, he knew what he was doing, even though he didn't finish high school. I would still recommend you finish high school, but 1895, a bit of a different time. And then focused beams of X-ray radiation can be used to shrink or eliminate tumors. That's radiation therapy. So radiation therapy is another use for X-rays that can be very helpful. If you're interested in learning a little bit more about X-rays, watch the video right here about X-rays and what they were and what they are and why they're so cool and why do we know so much about X-rays? Because they're probably one of the most famous forms of electromagnetic radiation up there. And the final one, the highest energy EMR out there, is called gamma radiation. They are emitted by radioactive materials, substances that spontaneously emit radiation from an unstable nuclei. We will discuss more about nuclear radiation and emission of this type of form of radiation in Unit D. When we get to the energy unit, we'll be discussing more about nuclear physics at that point. But for now, be aware their energy level is very high, just as Bruce Banner in the Marvel series, The Incredible Hulk, right? He used gamma radiation. That isn't what's going to happen. If you expose yourself to gamma radiation, you're not going to turn into the Hulk. You're just going to turn into a really bad piece of flesh with a lot of damaged DNA that's probably going to kill you. Effects on biological tissue. Well, again, it's a severe physical mutagen to DNA, like I just mentioned. There is one use of gamma radiation that we make use of. There is one of these in the University of Alberta. They have what's called a gamma knife, a radiosurgery. It's a type of radiation therapy used to treat tumors, especially brain tumors in the brain, because you can very precisionally target this EMR to attack small pieces of tissue inside the brain, and it basically just destroys the tumors that are there. But again, it has to be very focused and very concentrated to one particular area, because if it gets into other parts of the body that it's not supposed to, it can cause a lot of trouble and a lot of problems. And that's it. That's our discussion about the electromagnetic spectrum and all the goodies associated with it. What's your homework related to it? Well, there's a few questions. You got questions 5, 6, 7, 8, 10, 11, 12, 14, 15, 17, 18, 19, 20, 21, 22, and 23 on pages 417 to 432 in the textbook. And you're going to answer questions 2, 3, 5, 8, and 9 on page 435 of the Science 30 textbook. So that'll be everything you need to know to cover the first half, the first half of the second half of Unit C. Join me again next time when I finish up the unit on electromagnetic energy, when I'll be discussing, I didn't hit it really well, come on, hit it one more time. I'm going to be discussing topic 2.2, which is astronomy. We're going to go into space and discuss a little bit about stars and other neat things, and we're going to get to, I'll let you wait till next time, but we're going to discuss stars, which is kind of cool. I do enjoy talking about stars. That's it for today, folks. Thanks for tuning in, and until next time, see ya later.